Le prochain présentateur est Yoandy Alonso Diaz, détient un diplôme de 2e cycle en physique de l'atmosphère et un baccalauréat en météorologie de l'Université de la Havane. Il a plus de 12 ans d'expérience à l'Institut cubain de météorologie et il s'est spécialisé dans les énergies renouvelables et l'étude des phénomènes climatiques. Pour sa thèse de doctorat, il a développé un modèle améliorant la précision de la classe des vents de Cuba. Chercheur postdoctoral à l'Université de Montréal, il analyse aujourd'hui la vitesse du vent et la couverture nuageuse au Québec à l'aide des modèles climatiques. Donc, à toi, Yoandy.
Okay, good morning, everyone. My name is Yoandy Alonso. Today we're going to talk about the methodological part of the project. This is the project we are involved with the part of the Professor James King, and also we work with Helen and Biana as well. In this small presentation, we're going to talk a little bit about the overall project. We're going to explain the methodology and the data source used in the research. And also we're going to evaluate some pre-analysis products and climate models like HIRES-MIP and North American Cortex. And the last part of the presentation will be about some feature simulations with the Cortex North American climate models. So, like we know, evaluation how well Earth system models and regional climate models simulate the surface winds is essential to better understand and predict the impact of climate change on the surface processes. While the ECMs provide insight into a global circulation and larger scale climate patterns, the regional climate models provide a more detailed representation of the local processes. The performance of both groups of models in simulating the winds depends of, among other things, the model resolution, the physical processes included, and the quality of data used to drive these models. In the Quebec region, our study domain, there is an ongoing debate about whether surface wind speed will increase or decrease in future, as different models and analyses produce different results. The overall project has three principal objectives. First, to analyze the trends of homogenized observed wind speed from all available Quebec meteorological stations and evaluate the performance of the reanalysis products for simulating wind surface. Second, to evaluate the skill of high-resolution climate model to simulate surface wind speed and direction in the Quebec region, and to evaluate the robustness of the signal of future simulated wind speed using high-resolution climate models on the different emission scenarios. But today, in this presentation, we're going to talk about specifically which reanalysis best represent the surface winds in Quebec region, which high-resolution modeling approach best represent the historical winds at surface, and how robust is the signal of change in future wind speed simulating for different model resolutions and scenarios. For doing that, we're going to study the Quebec region. The domain is in the Quebec region, and we will have a set of 26 meteorological stations for wind speed, 10 from MLCC and the rest from Environment Canada, and another set from 18 meteorological stations for the wind direction. Also, we're going to use and analyze 4 of the most common reanalysis products used from the historical period of 1980 until 2010. These products are ERA5, NAR, and CEP and CAR, and MIRA2. It's important to mention here that the analysis is based on the monthly mean values of wind speed and wind direction in all the analysis. We will evaluate as well a set of HIRES-MIP global models, coupled surface temperature, from the same historical period. And in this case, we have the models divided in 2 groups, the medium resolution group and the low resolution group, depending, of course, on the resolution of the model. These resolutions are like 50 kilometers and 100 kilometers. Also, for future projections, we have another set of ESNs interpolated to 100 kilometers for making ensemble in the two future scenarios, RCP 4.5 and RCP 8.5. And with these models, we will be used for driving the last sets of models used today, which are the North American cortex for future periods until the period of 2010 until 2100, with two sets of different resolutions, the 22, like 25 kilometers, and the North American 44, like 50 kilometers in both sets of future scenarios, 4.5 and RCP 8.5. So the metrics used in this evaluation would be the mean error and biases. Also, we use the Taylor diagrams. Taylor diagrams is a plot that use three metrics, and it graphically puts three metrics: the correlation, the standard deviation, and the root mean square error. So we could here evaluate a set of a group of all models together and compare them with the reference that would be stations, and as close as the model is to the reference, the performance would be better. Also, we use the Perkin skill score that this score measures the degree of overlap between the probability density function, probably the probabilistic, the density function from the observation, the black line in this case, and the different models. So this score goes from 0 to 1. As close to 1, the Perkin score is, the performance of the model will be better. And for the assessment, the robustness of the climate change for the future projections, we will use the methodology from the IPCC that has three classifications: the robust signal, no change and no robust signal, and conflicting signals. So to answer our first question, which analysis best represents the surface wind speed in the Quebec region, we will evaluate the four reanalysis products used in this research, which are ERA5, NAR, and SAPE-CAR, MERA2. And we have the mean absolute errors in this graph and the estimate wind speed. So every model is represented of the color at the 26 meteorological stations from the historical periods. We can see that the most of the reanalysis trends to overestimate the wind speed in our story region, especially MERA2. Especially MERA2, which overestimate the surface wind speeds up to around more than 3 and up to 44 meters per second. Okay. Our second analysis will be based on the biases of the four reanalysis products. We can see here the spread of the biases in the different locations. We have the ERA5, NAR, and SAPE-CAR, and MERA2. We see like red colors represent overestimation of the wind speed, and blue colors represent underestimation. We can see that some of the larger biases during almost in all the reanalysis products are located in complex terrain stations and in coastal areas. For example, Gaspé, right here is represent an overestimation in almost the three reanalysis products, except for ERA5, that present the less biases with the light blue and light colors in the southern of Quebec region. For the Perkin score analysis, it's important to mention that the wind speeds is represented in the colored box plots, and the wind direction in the white box plots. So as close to 1, we have the result of the Perkins skill score. The representation of the wind speed compares with the station would be more skill. So we can see that Mera 2 has the less representation of the stations. Also, the wind direction, the white box, is fully represented by all the reanalysis, around 0.5, more or less. And again, ERA 5 is the reanalysis that best represents observed wind speed up to 0.8 Perkins skill score. So, like ERA 5 was the best reanalysis in these 3 tests that we are making today. From now, we're going to choose the reanalysis ERA 5 like the reference. So, which high resolution modeling approach best for represent the wind and its surface? Now we're going to make the same metrics that we made before for the reanalysis product, but in this case with the higher Smith models. So we have a block that compares the Perkins skill score of the rest 3 reanalysis product with ERA 5, and also we have the Perkins skill score for the group of the medium resolution higher Smith and for the low resolution higher Smith. Again, the colored boxes represent the wind speed, and the white ones the wind direction. We can see that the group from the higher Smith models show the best performance in capturing the wind distribution compared with our reference now, ERA 5. The second the second metric we're going to use here is the Taylor diagrams that shows the correlation, standard deviation, root mean square of the models compared with the reference. The reference would be ERA 5. Also, we have the 3 reanalysis in this analysis as well, and the group of the higher Smith models represented by the small dots, colored dots. The ensemble of these models with the black small diamond, and also with the low resolution models with bigger dots, and the ensemble with the largest black diamond. So we have 2 diagrams. The left diagram is made with the entire domain, so the land portion and ocean as well. And the second diagram, the right side, is use the grid points in land only. So we can see here that there is a higher spatial correlation and lower errors when considering land with ocean grid points compared to the bigger spread of the models in land only. But for both, the medium resolution consistently outperforms lower resolution models and the analysis products. So we can see that the small dots and their ensemble in both cases is closer to our reference, showing better skill. The same analysis we're going to perform now, but with another group of models. We have here the set of the North American Cortex high resolution models and also the medium resolution models. And in this case, we have the same analysis product, but we divide it depending on the drivers of the model. So we have this small section, this North American high resolution model, but driven by interim, which is a reanalysis as well. And the same thing here, but with the medium resolution. We can see here that the models driven by ERA interim perform similarly to models driven by the ECMs. So there is not a big difference between in this experiment. There is not too much difference with models driven by reanalysis product and models driven by ECMs. Both high resolution and medium resolution models perform similarly in the sense of the CM5 DMCM5s are the colored in blue, the UCAN version, and the purple, the Uranus version. It's important to mention here that the wind direction is better represented in this case, but like we compare them with ERA5 at the same time doesn't represent very well the wind direction in our solar domain. So it's good to keep it on mind. The same analysis of this group of cortex, high and medium resolution model, but in this case, the Taylor diagrams, the same idea, the 4-3 analysis compared with ERA5, a group of high resolution North American models and their ensemble with the small diamond, and another set for medium resolution and their ensemble. So we have the land only and land plus ocean Taylor diagram, and we see that during the land and ocean domain has the higher spatial correlation as well. But the medium resolution models outperforms the medium high resolution. The medium resolution models outperform high resolution on land, but are similar for land with ocean models. So we see a group of the models with the biggest dot that represent the medium resolution with a better representation in land only, but during the entire domain, there is not the same behavior. So world-based simulations are the least in this case, compared with ERA5. And finally, CRCM5 based models have a good spatial correlation and higher spatial variability, both of them. Also, the UCAN and the Uranus version compares with the rest of the North American cortex models. Put them all these ensembles in one relative bias. We have in blues the Hyder-Smith coupled models, low and medium resolution, and in red the North American models, high and medium resolution. We could see that in the summer months, North America has the largest biases, up to 40% in August, and Hyder-Smith medium resolution models show the smaller biases represented with this light blue in almost all the season of the year and annually, compared with the rest of the months. Putting this in the map, in the location of the stations, we see that all the model ensembles perform similarly, equally well in the southern of Quebec, showing the light color areas, but it's still difficult for the model to simulate complex terrain in coastal locations, like Gaspé, in this case, still being difficult for them. And the Hyder-Smith medium resolution perform best with ERA5 over the range of stations locations. Putting all these metrics that we have used today together, we build a ranking of these models and also the reanalysis products and the ensembles of the models. So in this case, this will be the ranking. Red color means best performance, and blue color means the worst performance. So we have the three metrics here. The first row would be the Taylor skill score. The second one, the Perkin skill score. And the third would be the mean absolute errors. So depending on these three scores, the ranking would be given to the model. We can see that the first four models of the ranking that are Hyder-Smith medium resolution, and we see clearly that the ensemble mean, the same symbol that we have used, the black diamond representing them, and also the Hyder-Smith medium low resolution is as well good in a good position, followed by the North American cortex medium resolution, North American cortex high resolution, and the three reanalysis products. Giving the least representative with ERA 5, the MERA 2. It's important to mention that this analysis was made in the Quebec region. So if we use another region of the planet, or even another region of the world, the ranking should be different. So the last part of this presentation today will be how robust is the signal of change in future wind speed simulated for different model resolution and scenarios. We have here a set of 5 ECMs for the two different scenarios, RCP 4.5 and RCP 8.5 at 4 different vertical levels, surface, a 50, 500, and 200 millibards. The historical period, the base period, from 1980 until 2010, and the future period from 2071 until 200. Sorry, until 2100, and we have the relative change of these vertical levels and the absolute change. And the same thing with the RCP 8.5. We see here that following the IPCC methodology, there is not robust signal of change in any of the levels, in any of the both future scenarios, except for a small point here, located in 200 millibars for the RCP 8.5. So, making the same analysis, but making the sort of short resume. With the annual, we have here the annual for the ECMs in the future with an ensemble of 5 members. For LCP 4.5, we have North American 44, the medium resolution with 6 members, and North American 22, the high resolution ensemble with the high resolution with the 5 members. So we can see that is still not significant change in any of these experiments annually or seasonally. But North American 44 and 22 project larger seasonal change in surface wind speed over the north part of the province during the months of summer and autumn. So there is no robust signal change, but could be some change up to 40% in these seasons. The same analysis, but in this case with the future scenario RCP 8.5, we have the same ensemble of the ECMs, but in this case, the members of the North American 44 are 14 and 16 for North American 22. There is no change in the annually, also no change in any of the seasons of the year. But like before, we have here, in this case, North American 22 projections up to 30 and 40% in the north part of the province. And like summary, we could see that today, in terms of mean of absolute error, mean biases, and Perkins skill score, ERA 5 performs the best of the evaluated reanalysis product when compared with meteorological section data of the Quebec region. Taylor analysis results in the hardest medium resolution models outperforming the other models ensembles in spatial correlation and the standard deviation when compared with ERA 5. North American cortex high resolution models provide good representations of wind speed in areas of complex terrain when compared with ERA 5 values for individual stations locations, and the systematic difference in surface wind output from both models approach when compared to ERA 5 highlight the criteria role of the boundary layer on surface roughness influencing model performance. And for the section of future projections, there are no robust signal of change in wind speed over the surface for the ECMs ensemble evaluated, except for a small region in the northeast Quebec at 200 millibars for LCP 8.5. There are no robust signals of the change in surface wind speed for all analyzed in the standard simulation, and also not robust signal, the mean ensemble similarity change in seasonal surface wind speed are the largest in summers and autumn in the northern Quebec, up to 40, 45 increase, and in a higher resolution model, SCP. So thank you very much.
Merci pour la présentation. I think it's super interesting and will be really useful to have this. Can you tell me more about the test for the robustness? How can you have like a 45% change, but it's like no signal for change, no robust signal? Can you explain a bit more how that works?
Yeah. This is a test for the robustness following the IPCC report. It is divided in 3 categories. The first one, robust signal, represented by colors. This signal is presented when the majority of the models show change greater than this variability threshold, and at the same time, the majority of the models agree of the signal essential. So for having a robust signal, we will have 2 things: change greater than the annual variability, and at the same time, agreement with the models. So, like we saw in almost all of the figures, we have no change or no robust signal because there is the minority of the models, the change greater than the variability threshold. This threshold is built depending on the internal annual standard deviation of the model.
Okay, so maybe there's one model that like pulls.
Yeah.
Thanks.
Chris?
Merci de la présentation. I was wondering if I guess I have a couple questions. The first one is you showed the reanalysis results, the MERIT 2, the NSEP. It looked like the NSEP car was much better than MERIT 2, even though it had a much lower resolution. I'm wondering if you have any idea what that might be from.
That is a good question. Like we see, the representation of the models doesn't depend on the resolution, because MERA2 is the third, like you mentioned, the third with the resolution. Most people use MERA2 like their reference. There is a lot of bibliography about that, but our test shows that in our province, in our case, maybe in another place, MERA2 performs better, but in our small domain, ERA 5 was the best. Is as well and also NAR and 7 cars. So I was really surprised as well, but I'm not a specialist in this kind of reanalysis. I don't know how they build it, and I can tell you exactly the reason.
You should look at the parameterization of the surface.
Maybe.
Right. But it's still weird because the mirror 2 also use the observation, so I don't know.
Yeah.
And I guess another quick question, it's already a lot of work, but have you looked into like higher spatial temporal resolution, like daily mean or daily max, that might be more correlated with?
No, in this case, like you saw in the presentation, there is a lot of models, a lot of group of ensembles, and I had to use the monthly means, because otherwise I should not have enough computer resources and compute time. We are running on time all the time, and I thought that would be enough for monthly mean value for representing the future, because like we saw previously in the presentations before me, that our goal is to study how will be the wind direction and wind speed for future. So I guess that for monthly, but it will be interesting to make this analysis with the higher resolution to see how will be the performance. But right now we are.
You began to process the time series. You're still in processing.
Yeah.
Est-ce que vous d'autres questions? D'autres questions? Est-ce qu'il y a des questions en ligne, Liliana? Moi, si je peux me permettre un commentaire, j'étais vraiment contente de voir que des modèles régionaux, même pilotés par des modèles globaux, performaient mieux que la plupart des réanalyses. Quand on vient de la modélisation régionale, c'est un résultat qui faisait plaisir à voir, même si c'est pas parfait. Les vents, c'est quelque chose de compliqué à réussir. Puis de voir que c'est comparable ou mieux que les réanalyses, ça a été une belle journée quand on a vu ces résultats-là. Donc, mais ça clôt les séminaires d'aujourd'hui. Merci encore, Yoandy, pour cette présentation. Merci encore à Patrick et Méga. Donc, est-ce que, je sais, je n'ai pas regardé.
Question pour Méga et Patrick, peut-être? Est-ce qu'il y a des questions pour Patrick et Méga?
Ben, merci beaucoup à tous. Merci aux participants en ligne et surveillez l'annonce de nos prochains webinaires. Merci à tous.